Okay, so we have this triangle. This is from the second slide on March 24th's lesson. The first thing I want to do is find all of the missing angle measures. So I'm going to start with this little right triangle. I have a 90-degree angle here and a 65-degree angle here. So I can find this little angle measure up here, and that ends up being 25 degrees. Moving over to this non-right triangle, it's an obtuse triangle. I'm going to start by finding the measure of angle ACD. I can do that because these two angles are supplementary, they're a linear pair. So 180 minus 65 gives me 115 here. And finally, again in this obtuse triangle, I can find that third angle measure, angle CAD, by adding these two together and subtracting from 180, and that gives me 45 degrees here. So I'm going to start by using law of sines for this obtuse triangle. I'm going to use law of sines because it's not a right triangle, so I can't apply SOHCAHTOA here. And I'm going to try and find AC because AC is the connector between this triangle over here and this little right triangle here. And ultimately, we're trying to find the length of BC. So if I can get one side length in this little triangle ABC, then I'll be able to determine what the side length for BC is. So I'm going to label segment AC as X. Now I know that this length down here, CD, is 15. So using law of sines, I'm going to apply that sine of one angle over its opposite side length would be equal to sine of another angle over its opposite side length. So the setup for that would be sine of 45 over 15 equals sine of 20 over x. X is what I'm looking for. So I'm going to cross multiply to solve for x. I'm not going to go through that whole process just to save time. Let's see, so I'm going to do 15 times sine of 20 divided by sine of 45. And remember, you should not be, what's what I'm looking for? You should not be rounding yet. You need to keep several decimal places here. And unfortunately, this isn't really to scale this picture because this 45-degree angle looks smaller than the 20-degree angle. So because of that, this length AC looks like it should be longer than 15, but it actually should not. This should be the shortest side of that triangle. So don't let that freak you out. Remember, on the Regents, everything will be to scale, but sometimes on Delta Math or other sites, things will not be perfectly to scale. So we should get that X, or the length of AC, is 7.255342. I'm going to round that 8 up to a 9. So now I have the length of AC. I'm going to switch over now and use this right triangle, ABC. So in this little triangle, now I have the hypotenuse. So to figure out the length of BC, you could do law of sines again, or you could use SOHCAHTOA here. Let me move this up a little bit. So to use SOHCAHTOA, I'm going to use the 65-degree angle. That's not the only way you could do it. That's just one way. But according to this 65-degree angle, I'm looking for, we'll call this Y, which is the adjacent side, and I have the hypotenuse. That's what I found over here, this 7.2, etc. So opposite over hypotenuse, we know, is cosine. So I'm going to set up cosine of 65 is equal to y over my hypotenuse, which I found before, 7.25534229. So to solve for y, I'm going to multiply both sides by 7.25534229. So cosine of 65 times that hypotenuse gives me that y is 3.06624. We'll round that to a 4. And you're asked to find segment BC's length to the nearest whole number. So that nearest whole number would be